Causality and instantaneous information explores the idea that information might be transferred faster than light, challenging traditional causality. It delves into pseudoscientific theories that suggest instantaneous connections, often lacking empirical evidence yet inciting curiosity. The exploration includes quantum entanglement and other phenomena where cause and effect appear nonlinear or simultaneous, questioning the limits of current scientific understanding. The basic principles of causality involve a cause and effect relationship, where one event leads to another in a linear sequence. This concept is essential in understanding how events are temporally related, creating a framework for predicting future occurrences. The principles are evident in everyday life and are integral to scientific theories like Einstein's theory of relativity. When a cause is B, it means that event A is directly responsible for the occurrence of event B, establishing a cause-effect relationship. This temporal sequence implies that A precedes B and that B is dependent on A for its occurrence. In science, establishing causality requires empirical evidence that consistently supports this sequential relationship. The arrow of time is crucial because it provides a direction to the flow of time, from past to future, which is fundamental to understanding causality. It reflects the irreversibility of processes like entropy, where systems naturally progress toward disorder. This directionality is observable in phenomena such as aging and the unidirectional flow of heat. In everyday experiences, causality is apparent in classical physical systems where actions lead to predictable outcomes. For instance, pushing a ball causes it to roll, illustrating a simple cause-effect relationship. These predictable patterns form the basis of scientific experiments and technological advancements, relying on consistent and repeatable results. Einstein's theory of relativity profoundly reshaped our understanding of cause and effect by introducing the concept of spacetime, where space and time are intertwined. It suggests that causality is not absolute but can vary depending on the observer's frame of reference, especially at speeds approaching the speed of light. This theory challenges the notion of a universal sequence of events, indicating that simultaneity is relative and dependent on observers' relative motion. The illusion of time posits that our perception of time as a linear progression may be fundamentally flawed, impacting concepts of causality. Some scientists argue that time could be a construct of human consciousness, with past, present, and future coexisting rather than unfolding sequentially. This could mean that cause and effect are not as rigidly bound as they seem, allowing for events to be interconnected in nonlinear ways. The subjective perception of time varies greatly among individuals, influenced by factors such as age, culture, and psychological states. This variability suggests that time is not an objective constant, but is experienced differently depending on personal context and mental state. Understanding these perceptions can shed light on why certain events seem to unfold rapidly or slowly, impacting our sense of causality. The block universe theory proposes that time is a static dimension, much like space, where all points in time are equally real. In this view, the past, present, and future exist simultaneously, forming a four-dimensional block where events are fixed, challenging the idea of change and progression. This fixed structure implies that causality is predetermined, with no room for randomness or free will. The concept of a universal present questions whether there is a definitive now that all observers can agree upon, given the relativity of simultaneity. In Einstein's relativity, the idea of a universal present is dismissed, as events that are simultaneous for one observer may not be for another. This raises profound questions about the nature of time and whether causality can truly be anchored to a single moment shared universally. In quantum mechanics, time does not always flow in a straight line as it does in classical physics, leading to paradoxes like retrocausality. Quantum phenomena such as wave function collapse suggest that events can be interconnected in a nonlinear fashion, challenging the traditional chronological sequence. Experiments show that particles exhibit superposition, where they exist in multiple states simultaneously, questioning the very nature of time itself. The concept of instantaneous information transfer raises questions about the limits of communication speed in the universe. Various theories explore whether information could be transmitted faster than light, bypassing the speed limitations imposed by relativity. This speculation often intersects with quantum entanglement, where particles appear to share information instantaneously regardless of distance. The speed of light is considered the ultimate speed limit due to its role in the framework of relativity, as articulated by Einstein. Light travels at approximately 299,792 kilometers per second, which sets a boundary for how fast information and matter can move across space. This constant speed is essential to maintaining the causal structure of the universe, ensuring that cause precedes effect. Experiments with entangled particles reveal a mysterious phenomenon where particles remain connected, sharing states instantaneously over any distance, known as quantum entanglement. Notable experiments, such as those conducted by Alan Aspect, demonstrate that measuring the state of one particle immediately influences the other. This instant connection challenges classical views of locality and suggests the potential for faster-than-light information transfer. The distinction between information transfer and correlation is crucial in understanding quantum phenomena. While correlated events imply a relationship, they do not necessarily mean information has been exchanged, as seen in entangled particles. Information transfer requires a measurable change in the state of a system as a result of another, while correlation can exist without direct interaction or communication. Thought experiments on superluminal speeds explore the fascinating idea that information or matter could travel faster than light. These experiments often utilize hypothetical scenarios that challenge the known limits set by relativity, such as tachyon hypothetical particles that move faster than light. Such explorations capture the imagination, suggesting paradoxical consequences like reverse causality, where effects precede causes. Quantum entanglement is often confused with instantaneous information transfer due to the phenomenon where entangled particles appear to affect each other instantly over any distance. This confusion arises because the correlation between entangled particles does not imply actual communication or transfer of information, which remains bound by the speed of light. The non-local behavior of these particles challenges classical intuitions, leading to misconceptions about the nature of their interactions. The basics of quantum entanglement involve the phenomenon where two or more particles become linked and share a quantum state, such that the properties of one instantly affect the other, regardless of distance. This peculiar connection is a result of quantum mechanics, where particles exhibit non-local interactions that defy classical explanations. An example of this is spin entanglement, where measuring the spin of one particle instantly determines the spin of the other, despite their separation. The Einstein-Podolsky-Rosen (EPR) paradox questions whether quantum mechanics is a complete theory by illustrating a scenario where particles appear to communicate instantaneously. Einstein and his colleagues proposed this paradox to argue that hidden variables might exist, governing the behavior of entangled particles in a deterministic way. Despite its initial purpose, the EPR paradox led to further exploration of quantum non-locality, challenging the concept of reality in quantum physics. Bell's inequalities demonstrate that no classical theory based on local hidden variables can fully explain the correlations observed in quantum entanglement experiments. These inequalities provide a framework for testing the predictions of quantum mechanics against classical expectations, showing that quantum predictions consistently violate them. This violation implies that classical explanations are insufficient, reinforcing the notion that the quantum world operates under principles foreign to classical intuition. In popular science, quantum entanglement is often misunderstood as allowing instantaneous communication between particles, which is not accurate. This misinterpretation stems from the non-local correlations observed, leading to the false belief that information can be transferred faster than light. Such misunderstandings create confusion about the nature of entanglement and its implications for causality and information transfer. The limits of quantum information highlight that entangled particles do not enable usable instantaneous communication due to inherent constraints. Despite their instantaneous correlations, the randomness of quantum measurements means no meaningful information can be transmitted without classical channels. These limitations ensure that causality remains intact, preventing faster-than-light communication. The no-cloning theorem states that it is impossible to create an exact copy of an unknown quantum state, thus preventing any form of signal transfer through cloning. This theorem ensures that quantum information cannot be duplicated, preserving the integrity of quantum communications. By prohibiting copying, the theorem upholds the limits of quantum communication, maintaining causality. Random measurements in quantum experiments yield unpredictable values, which cannot be used to convey meaningful information. The inherent uncertainty in quantum mechanics means that measuring an entangled particle state results in a random outcome. Consequently, this randomness restricts any attempt at information transfer through entanglement, reinforcing the boundaries of quantum communication. Classical channels play a crucial role in quantum experiments by providing a means to coordinate and verify quantum communication. Although entangled particles share instantaneous correlations, classical communication is necessary to ensure that observers can compare and interpret their results. This reliance on classical methods underscores the limits of non-local quantum effects for practical communication. Many misunderstood experiments in quantum physics fuel popular myths about instantaneous information transfer. For instance, the Einstein-Podolsky-Rosen (EPR) experiment is often wrongly interpreted as proof of faster-than-light communication. These myths persist despite scientific clarifications that correlations in quantum entanglement do not equate to actual information transfer. The concept of spacetime fundamentally influences causality by intertwining space and time into a single continuum. Within this framework, events are ordered by their light cones, which delineate regions of causal influence based on the speed of light. This structure ensures that causal relationships are maintained, preventing any information from traveling faster than light. Light cones serve as a visual representation of the limits on causal interactions in spacetime. They define the possible future and past events that can influence or be influenced by a specific point in space and time. By establishing these boundaries, light cones prevent instantaneous information transfer, maintaining the integrity of causal relationships. Relativity challenges the absoluteness of cause and effect by introducing the concept of relative simultaneity. According to Einstein's theory, observers moving at different velocities may disagree on the sequence of events due to the warping of spacetime. This leads to scenarios where causal sequences are not universally agreed upon, dependent instead on observers' frames of reference. Black holes act as a one-way causal barrier due to their event horizons, beyond which no information or matter can escape. The event horizon represents a point of no return, where spacetime curvature becomes so extreme that escape is impossible. This creates a unidirectional flow of causality, where information can enter but cannot leave, reinforcing the limits of causal influence. Wormholes are theoretical passages through spacetime that could create shortcuts, potentially allowing for faster-than-light travel. If traversable, wormholes might enable events to influence others instantaneously, disrupting the traditional causal order. This concept remains speculative, with significant challenges such as stability and exotic matter requirements preventing practical use. Speculative theories on faster-than-light information transfer include concepts like tachyons and negative energy. These pseudoscientific ideas often lack empirical support but provoke interest by suggesting mechanisms that could bypass relativity's constraints. While such theories are intriguing, they remain largely theoretical, with no current evidence supporting their feasibility. Tachyons are hypothetical particles that are theorized to travel faster than light, potentially enabling reverse causality. Their existence would challenge Einstein's theory of relativity, which enforces the light speed limit. Although no experimental evidence has confirmed tachyons, they remain a popular subject in theoretical physics discussions. Negative energy, arising from quantum fluctuations, is considered a potential mechanism for phenomena like wormholes and exotic propulsion. Theoretical constructs such as the Casimir effect suggest that negative energy might be harnessed, although practical application remains speculative. This concept is pivotal in theories that explore altering spacetime to achieve faster-than-light travel. The idea of consciousness as a non-local phenomenon suggests that it might operate beyond traditional spacetime constraints. Some theorists propose that consciousness could be linked to quantum processes, potentially allowing for instantaneous interactions. This speculative view challenges conventional notions of locality and causality, although it remains without empirical support. Feedback loops in time suggest that information might travel backwards, challenging the conventional flow of time. In speculative scenarios, this could allow for retrocausal effects, where future events influence the past. Researchers have explored concepts like closed time-like curves, which theoretically permit such backward information transfer, raising questions about causality violations. Causality violation poses significant issues in physics, disrupting the chronological order of events. It challenges fundamental principles, such as the second law of thermodynamics, which relies on a consistent arrow of time. These violations could lead to paradoxes and inconsistencies, undermining the predictability of physical laws. Time travel creates paradoxical situations because it allows for events to occur in a nonlinear sequence. The classic example is the possibility of altering past events, leading to self-contradictory scenarios. Such paradoxes challenge the consistency of known physics, requiring hypothetical resolutions that often remain speculative. The grandfather paradox illustrates a situation where a time traveler could prevent their own existence by altering past events. Potential resolutions include parallel universes or timelines, where changes create separate realities. Another approach is the Novikov self-consistency principle, suggesting that events are constrained to prevent paradoxes. Consistency conditions are nature's way of preventing causality violations by ensuring that events remain logically coherent. These conditions posit that the universe inherently restricts paradoxical outcomes, maintaining a stable causality framework. Theories like the chronology protection conjecture propose mechanisms that safeguard against disruptive causal loops. The multiverse theory suggests that every decision or random event spawns a new universe, each with its own version of reality. This concept, combined with the idea of self-consistency, proposes that all possible outcomes occur, yet remain coherent within their own universes. Such theories offer alternative perspectives on causality violation, where events might not adhere to a singular, linear timeline. The intersection of consciousness and quantum mechanics explores how human perception might influence or be influenced by quantum states. Speculative theories propose that consciousness could collapse quantum wave functions, suggesting a role in shaping reality. These ideas, while lacking solid empirical backing, question whether the mind operates on a quantum level, potentially linking to phenomena like entanglement. The orchestroar theory, developed by Roger Penrose and Stuart Hameroff, posits that consciousness arises from quantum processes within neuron microtubules. This controversial theory suggests that quantum coherence in the brain structure contributes to conscious awareness. Critics argue that the biological feasibility of such quantum effects remains unproven, yet the theory continues to provoke debate. Quantum entanglement raises the question of whether consciousness can harness this phenomenon to achieve non-local communication. Some theorists speculate that the mind could use entangled states to connect with distant thoughts or entities. Although intriguing, the lack of empirical evidence and the constraints of quantum mechanics challenge the practicality of such ideas. In quantum mechanics, the act of measurement is believed to play a crucial role in determining the state of a quantum system. The observer's involvement suggests a participatory universe, where consciousness might influence the outcome of quantum events. This notion challenges traditional views, proposing that the observer is not merely a passive witness but an active participant in the fabric of reality. Consciousness source as a potential source of non-locality suggests that the human mind might operate beyond conventional spacetime boundaries. Some theories propose that consciousness could be linked to quantum phenomena, enabling instantaneous interactions or connections.